In section 4.2, linear combinations of vectors, we're going to continue our discussion of some of the concepts that we learned earlier in the course with vectors from Rn in a more general setting. So first we'll start with the definition of a linear combination, and I should point out that this definition of a linear combination is exactly the same definition that we used earlier in the semester, but now instead of just looking at vectors from Rn, we're going to be looking at other kinds of vectors too. So let's just go over it first. Suppose that you have a list of vectors v1, v2, up through vm, from some vector space V, and this can be any vector space. Then we say that this other vector V is a linear combination of V1, V2 through Vm if there are scalars, and notice that the number of scalars matches the number of vectors. So if there are scalars such that this equation works. So V, the vector that we're interested in, is equal to C1 times V1 plus C2 times V2, all the way up through Cm times Vm. So this is the same kind of linear combination that we've been looking at the whole semester, but now instead of just vectors from Rn, these could be things like matrices or functions or something even stranger. So our first example, as we try to understand this new definition, is to look at the vector space of 2 by 2 matrices and then look at linear combinations. And in particular, in this example, we want to determine whether this 2 by 2 matrix, 5, 5, 7 minus 10, is a linear combination of these three other matrices. That's 1, 3, 2 minus 4, 0, 1, 3, 2, and then the third matrix is 1, 0, 2, 0. So let's think through what this means. So going back to the definition, we must determine if this equation has a solution. So I have my vectors, matrices in reality, in this example. My three that I'm seeing, that I'm checking to see if form a linear combination of this matrix. And then I have my scalars here. So each matrix is being multiplied by a scalar. And we have to see if there are three scalars that solve this equation. So this leads to actually a system of 4 equations in 3 variables. And let me explain how. In order for both sides of this equation to be equal, each of the corresponding entries has to be equal. That means 5 has to be equal to whatever the upper left entry is from over here. And we can work that out. It's C1 times 1 plus C2 times 0 plus C3 times 1. So that gives us one equation that I've written down here. And then we'll get another equation for each other entry. So the second equation would come from this entry. 7 has to be equal to C1 times 2 plus C2 times 3 plus C3 times 2. And then take a look at the bottom left entry to get the third equation. And then for the fourth equation, you'll look at the bottom right entry of the matrices. So there's one equation for each entry in our matrices. And now that we have this translated into a system of equations, and notice that they're linear equations, we can make this into a matrix, an augmented matrix, and row reduce in order to solve for the constants, the scalars C1, C2, and C3. So here I've just translated the coefficients into an augmented matrix on the left side, and then this is the right side of the equation. So just like normal, And then I've omitted the row reduction steps since this is something that we've done so often. But it does end up working out. So when you go through the process of row reduction, you get this new augmented matrix, and we can just read off the solution from it. We can see that C1 is equal to 2, C2 is equal to minus 1, and C3 is equal to 3. And I've written that down here below. So since this system of equations had a solution, that means that these values for the scalars give a solution to this original equation involving matrices. So something that you should do on your own is just double check that that solution actually works. So plug in the numbers here and make sure this equation works out. And before we finish with this video, I want to do one more example with a different kind of vector space. In this problem, we're looking at polynomials. And if you remember from the previous section, we're actually going to be looking at a subspace called P2. So these are polynomials with degree at most 2. Okay, so this is a similar kind of problem to the last one. I want to determine whether this polynomial f of x equals 2x squared plus 3x plus 3 is a linear combination of these other two polynomials, g of x equals x squared plus 2x plus 1, and h of x equals x squared plus x plus 1. So we're still solving an equation, but this time our equation has polynomials. I want to see if this one, f, is a linear combination of the other two. So that means I have to see if there are scalars c1 and c2 that satisfy this polynomial equation. And this also leads to a system of equations, and let me explain how. If two polynomials are going to be equal to each other, that means that the coefficients on each power of x have to be the same. So on the left side I have a 2x squared. That means if I go over to the right side, the power or the coefficient on the x squared term must also be 2. And we can read off what that coefficient should be. It should be c1 times x squared plus c2 times x squared. So that means we get c1 plus c2 should be equal to 2. And then you would want to look at the linear coefficient, the x to the 1 power. Over here we have a 3x. On the right we'll have c1 times 2x plus c2 times 1x. And that leads to the second equation, 2c1 plus c2 is equal to 3. And then for the third equation, there's a small error here. Go ahead and fix that. Should be a 3. We can read off this equation too. Over here we have a 3 on the left side, and on the right we have c1 times 1 and c2 times 1. So that's where the third equation comes from. But what you should notice is that this system of linear equations can't possibly have a solution. We don't have to go through the process of row reducing, because this first equation, c1 plus c2 equals 2, can't happen at the same time that c1 plus c2 is equal to 3. That's just not possible. So we know that these two equations can't both have a solution, and the system also can't have a solution. So what that means is that our polynomial f is not a linear combination of g and h, because there isn't a way to pick scalars c1 and c2 that make this equation true.